This presentation is directed towards the service technician responsible for maintenance of the Hewlett Packard models 1310A and 1311A high-speed graphic displays. The 1310 and 1311A are large-screen electrostatic deflection displays. They're designed primarily for use as visual output devices in computer graphics systems, automatic test systems, medical systems, and similar applications. Subjects to be discussed include mechanical layout, signal flow to the block diagram level, unique specifications and adjustments, and a demonstration of CRT removal. Electrically, the 1310 and 1311 are identical, differing only in CRT size and front panel control locations. The 1310 has a 19-inch CRT with front panel controls across the bottom for focus, astigmatism, position X, position Y, power on indicator, and intensity. The 1311 has a 14-inch CRT with the same controls mounted vertically along the right side. By loosening two screws, removing the intensity knob, disconnecting the quick disconnect plug for the power on indicator, the plastic mask can be removed. This exposes other controls used less frequently: orthogonality, trace align, gain X, and gain Y. On the rear panel are the power on switch, line input and voltage selector, and X, Y, and Z axis signal input connectors. The bottom side of the instrument exposes the low voltage power supply, high voltage regulator, and high voltage rectifier. Notice that most board connections are made with edge connectors, permitting convenient board removal. Here's the CRT post-accelerator connector. Anytime this is disconnected, it should be discharged to ground immediately as a safety precaution. All other circuitry is located on the top side. Z-axis amplifier, Y-axis input, Y-axis output, X-axis input, X-axis output, and focus astigmatism board. An extender board is also provided. Now let's discuss signal flow. Here's a simplified block diagram showing the X and Y-axis input and output deflection amplifiers. The Z-axis amplifier, which provides intensity and blanking control for the CRT, a low voltage power supply, and a high voltage power supply. The low voltage power supply is a standard regulated supply configuration. The AC line voltage is stepped up, rectified, and applied to series regulating devices which maintain constant output levels regardless of line or load variations. The low voltage supply provides plus 15 volts, minus 15 volts, and plus 250 volts. The high voltage power supply provides the necessary voltages for the CRT. Plus 15 volts from the low voltage supply provides operating bias for an oscillator circuit, which drives a step-up transformer. The high voltage AC developed on the secondary winding is rectified, filtered, and applied to the CRT cathode and control grid. The high voltage AC is also applied to a voltage octupler, where it's rectified and multiplied by a factor of 8. The 24 kilovolt output is applied to the CRT post accelerator. The output level of the secondary winding is monitored by an error detector. If the voltage varies from normal, the detector provides a correction signal to the oscillator to change the primary voltage, compensating for the variations. Now let's examine the high voltage supply in more detail. The quiescent grid-to-cathode bias is developed across R4, part of a DC restorer circuit. The 50 kHz AC output from the oscillator is transformer coupled through a current limiting resistor and coupling capacitor into the DC restorer. On 1/2 cycle, current flows through CR3 and R4. On the other half cycle, current flows through CR2. The voltage drop developed across R4 provides a negative voltage on the grid of the CRT. Looking at a more complete schematic, we find that the Z-axis amplifier is tied into the circuit through clamping diode CR4. The intensity limit pot is connected into the circuit through clamping diode CR5. During the positive excursion, the AC voltage at this junction will be clamped by CR5 to the DC level established by the intensity limit pot. And, during the negative excursion, the voltage is clamped by CR4 to the DC output level of the Z-axis amplifier. Therefore, the voltage drop across R4 will be a function of the difference in voltages between the intensity limit pot and the output of the Z-axis amplifier. For example, if the Z-axis amplifier output is at 60 volts and the intensity limit pot is set for 100 volts, then the voltage excursion at this junction will be 40 volts. Since the grid voltage is always referenced to the fixed cathode potential, the grid will accurately track the output of the Z-axis amplifier. The focus grid circuitry is similar. Next, let's discuss the X and Y axis deflection circuits. The inputs are fully differential. A triaxial cable is used, with a center conductor going to one side of the input, the shield going to the other side, and a grounded shield around both of these. Instruments are shipped in a single-ended configuration, but are easily changed to differential operation by changing this resistor value from 47 ohms to 10 k ohms. X and Y deflection factors can be varied by removing these jumpers and changing these resistor and capacitor values. Section 3 of the Operating and Service Manual provides complete instructions for these modifications. Input impedance can be switched between 10 k ohms and 50 ohms with this switch. Here's where the switches are located on the X and Y axis input amplifier boards. Incoming signals are coupled through impedance converters and amplifiers to a current controlling device where signal gain is controlled. Because of the large physical size of the displays, cable length poses a major problem. For this reason, a DC-controlled electronic attenuator is used to vary signal gain. Let's look at the first stage of the deflection amplifiers without gain control. After passing through the impedance converter, the input signal is applied to the bases of U1, Q1, and U1, Q2. The signal current, I1, through the emitter resistance is the input to operational amplifier Q8, A, and B. Here's the same circuit with the electronic attenuator added. Signal current I1 is now divided into two parts. One part flows through U2, Q3 and on into the operational amplifier. The remainder is diverted through U2Q4 and then shunted out of the circuit. By varying the DC bias on U2Q3 base with a front panel gain pot, we control how much current is coupled to the operational amplifier or is shunted out of the circuit. The operational amplifier output is applied to a differential amplifier and then to the CRT deflection plates. Deflection signals are also applied to other circuits for dynamic focus and astigmatism control. Another output, a logic signal, is sent to the phosphor protection circuit. We'll discuss these circuits later. The Z-axis circuitry controls the brilliance of the display. The rear panel Z-axis input signal and the front panel intensity control together vary the voltage on the CRT control grid. Input impedance is selectable here too, 10 k ohms or 50 ohms, with this switch on the Z-axis amplifier. Pads are also provided for adding an input attenuator. Incoming signals are coupled through a source follower to a double-ended current amplifier. This permits selection of either positive or negative signals for blanking control. Here's the switch on the Z-axis amplifier board. The current amplifier output is summed with the intensity pot current, amplified, and applied to the CRT control grid. With no external signal applied, the Z-axis is controlled entirely by the intensity pot setting. Another input to the Z-axis circuitry is from the phosphor protection circuit. This circuit monitors the outputs of the X and Y deflection amplifiers and operates similar to an OR gate. One of these two inputs must always be present to keep the phosphor protection circuit in an inactive state. If there's no deflection on either axis, indicating a stationary beam, the phosphor protection circuit will activate and limit the Z-axis output level to prevent CRT burns. An on-off switch, located here, allows the phosphor protection circuit to be disabled. However, in normal applications, this is not recommended. Our next subject is the dynamic focus and astigmatism circuits. As the electron beam is deflected away from center screen, the distance it must travel before striking the phosphor increases. In other words, beam 1 doesn't have to travel as far as beam 2 to strike the phosphor. This action causes a slight defocusing of the display. This problem can be minimized by varying the focus and astigmatism voltages as the beam is deflected. If we plot the change in focus grid voltage required to keep the spot in focus as the beam is deflected from center screen to either side, or from center screen to top or bottom, the curve will be parabolically shaped, with the least positive voltage at center screen. It's also symmetrical. That is, the change for a given movement to the left is the same for a similar movement to the right, or up or down. The curve is shaped the same for both the astigmatism and focus elements. The dynamic focus circuitry converts the linear deflection voltages from the X and Y amplifiers into parabolic voltages with non-linear amplifiers. The outputs are summed, combined with a front panel focus signal, amplified, and applied to the CRT focus grid. Similar circuitry is used for dynamic astigmatism control. This concludes our block diagram discussion. If trouble occurs, first check the low voltage power supply and then the high voltage power supply. Remember that the operation of the plus and minus 15 volt supplies and the high voltage power supply is dependent on the output level of the plus 250 volt supply. If the high voltage power supply output levels are incorrect, the CRT won't function properly. If trouble is suspected in either the X or Y deflection circuits, remember that the circuit boards are identical and can be interchanged for convenient troubleshooting. Next, we'll discuss several specifications that are unique to large screen display devices. First, linear writing speed. This is specified at greater than 10 inches per microsecond on both instruments. This means that the beam can be deflected in any direction at a speed of 10 inches per microsecond with less than 1% of nonlinearity. Both instruments will write faster than this, but with degraded linearity. Next, diagonal or large step settling time. For any given deflection command, the spot will be deflected to less than 1 spot diameter of its final location in less than 1 microsecond. Closely related to diagonal settling time is sequential point plotting time, or small step settling time. This spec means that when 1/10 inch stepping commands are applied, the beam will be within 1/100th inch of its new position within 200 nanoseconds. Repeatability. When the deflection inputs are repeatedly returned to any arbitrary voltage levels from any on-screen position, the beam will always return to the same point on screen, within 0.15% of full screen deflection. Finally, brightness. This specification is difficult to measure since most users don't have the necessary equipment. However, a simple diagram of the test setup looks like this. The instrument is set up to display a horizontal line at a writing speed of 0.1 inches per microsecond at a 60 Hz refresh rate. A scanning spot photometer is mounted in front of the instrument and is adjusted to scan vertically across the displayed line. The X and Y outputs of the photometer are connected to an XY recorder. The resulting recorder plot will look something like this, with brightness plotted against vertical position. Before making the measurement, the graph is calibrated for 0, 50, and 100 foot Lamberts using a standard light cell reference. Hewlett Packard guarantees that this peak, representing maximum brightness, will be at least 50 foot Lamberts. However, if the trace isn't focused correctly, the trace will widen, the curve will flatten out, and the spec may not be met. Since brightness is directly proportional to refresh rate and inversely proportional to writing rate, if either of these factors are changed, the brightness will also change. One point to remember: all specifications apply only to the quality area. The center 11 by 11 inches of the Model 1310A and center 8.5 by 8.5 inches of the Model 1311A. Now let's discuss unique adjustments. First, remove the static charge that's present on the CRT glass. With power on, hold the chassis with one hand and rub the other hand across the face and top of the CRT. This eliminates being surprised by a low current arc later. This charge can't hurt you, but it is unpleasant and might cause you to jerk while making an adjustment. Our first adjustment is Z-axis balance. Check to see that the phosphor protection switch is set to on. Now, with no X, Y, or Z-axis signals applied, adjust the intensity control until a dim spot is observed. Next, switch the Z-axis polarity switch between plus and minus while adjusting the Z balance pot for no change in spot intensity between positions. To adjust the dynamic focus and astigmatism circuitry, center the focus and astigmatism controls and position the spot to the center of the CRT. Next, connect a voltmeter to test point 1 on the focus astigmatism board. Adjust the focus balance adjust for an indication of plus 50 volts DC. If a dot pattern generator is available, connect it to the display and adjust it for a full screen raster of dots. If a dot pattern generator is not available, the dot can be manually positioned to each point of adjustment. First, locate the corner of the screen that has the best appearing spot. Leaving the focus and astigmatism control centered, adjust the focus limit adjust and astigmatism balance adjust for the best focused and roundest spot in that corner. Next, locate a spot halfway toward center screen along the X-axis and adjust X-axis astigmatism adjust number 1 and X-axis focus adjustment number 1 for the best spot at that location. Move the spot to the center of the screen along the X-axis and adjust X-axis astigmatism adjust number 2 and X-axis focus adjust number 2 for the best appearing spot. Now move the spot halfway toward center screen along the Y-axis and adjust Y-axis astig adjust number 1 and Y-axis focus adjust number 1 for best spot. Lastly, position the spot at center screen and adjust Y-axis astigmatism adjust number 2 and Y-axis focus adjust number 2 for best spot. This concludes our discussion on adjustments. All other adjustments are similar to those in standard oscilloscopes. Our final topic is CRT removal. We'll use a Model 1311A for demonstration. However, the procedure is the same for both instruments. First, remove the CRT base socket and loosen the clamp. Next, disconnect the neck pins. Disconnect the post accelerator lead and immediately discharge it to ground. Remove the screws attaching the post accelerator connector to the deck. Remove the plastic mask and the 4 screws that attach the CRT to the front of the instrument. Now carefully slide the CRT out, being careful that the neck pins don't catch on the coils located inside of the shield. Since these large screen displays are used in a wide variety of custom systems, you will probably see quite a few special versions. All of these use basically identical electronics, with only minor modifications. For instruments that do vary significantly from the standards, be sure to refer to the special documentation for the particular instrument. During the last few minutes, we've discussed the Hewlett Packard Models 1310A and 1311A, physical layout, general signal flow, some of the specifications and adjustments, and CRT removal. Now let's test our knowledge of the instruments by answering a few questions. Answer carefully, and stop the recorder if necessary to give yourself time to answer. First question. Before removing the CRT or working on the high voltage power supply, what safety precautions should be observed? Your answer should have been, discharge the post-accelerator lead to ground. This lead has 24 kV on it, and the power supply will hold this charge long after the power has been removed, unless it is discharged. Next, briefly explain the purpose of the phosphor protection circuits. The phosphor protection circuit protects the CRT from burns that could be caused by a stationary or slow-moving beam. It does this by limiting the output of the Z-axis amplifier. In most applications, this switch should always be in the on position. Let's try this one. A malfunction has occurred, and we have no X-axis deflection. What can we do to further isolate the problem? Since the X and Y-axis circuitry is identical, the Y-axis preamp and output boards can be substituted with the X-axis to isolate the trouble to one of the two boards. From here, normal troubleshooting procedures can be used. Next, if the high voltage malfunctions, our first check should be to see that the low voltage is okay. True or false? You should have answered true. The high voltage power supply is dependent on the low voltage power supply for its operating voltages. Last question. What does the specification diagonal settling time or large step settling time refer to? This spec means that for any given deflection command, the spot will always be within one spot diameter of its final location in less than 1 microsecond.